2.2 D'Alembert's principle of virtual work. This section summarizes D'Alembert's argument in modern notation according to: suppose the system is in equilibrium, i.e. f vector sub I equals 0, then clearly f vector sub I dot delta r vector sub I equals 0. So, the sum from 2 of f vector sub I dot delta r vector sub I equals 0, which we now decompose as
equation 2-5, where f vector sub I is the applied force and f sub I is the force of constraint. Thus,
see the next equation, where the delta r vector sub I can be arbitrary displacements. We now restrict to the situation where the net virtual work due to the forces of constraint is 0, normal sigma sub I vector sub I dot delta r vector sub I equals 0, to then get
normal sigma sub I vector sub I dot delta r vector sub I equals 0. Suppose the system is now in a general setting, f vector sub I equals dot p vector sub I, if we split off the force of constraint as before.
See the equation shown. And, with the same assumption of 0 net virtual work due to constraints, we get
equation 2-6. From the above form we must transform to generalized coordinates that are independent of each other, such that the coefficients of the displacements can be set to 0 separately.
See the next equation. First consider the transformation of the f vector sub I dot delta r vector sub I part, dropping the applied superscript.
Equation 2-7. Where the dimension of Q need not be the dimension of the force, nor the generalized coordinates the dimensions of length, but their product must still be the dimension of work. Now let's consider the transformation of the term.
Now, furthermore, switching to dot r sub I vector equals v sub j vector. See the equation shown. We can now write.
See the next equation. And writing the kinetic energy term normal sigma sub I raised to the power 1/2 m sub I v vector sub I squared equals t, we get D'Alembert's principle in the form.
Equation 2-8. Using force written in terms of a potential function, where equipotential surfaces are well defined in relation to field lines, we have
equation 2-9. If we now introduce the standard Lagrangian L equals t minus v, we find that D'Alembert's principle gives rise to the equations of motion expressed in terms of the Lagrangian.
Equation 2-10, where the latter succinct form of the equations of motion are known as the Euler-Lagrange EL equations. This completes the derivation of the EL equations by way of D'Alembert's principle. We will perform a different derivation of the EL equation in the context of Hamilton's principle of least action in the next chapter.
Let's now consider some of the simplest force fields or phenomenology. Suppose the force acts in a single direction, uniformly, and is constant. Such would be an example of the force due to gravity at the Earth's surface, where F equals negative mg. When taken with the simple pendulum we have a complete description since all other system parameters involve the pendulum, arm length, which is massless, and pendulum bob mass. Example 2.1. The simple pendulum. Figure 2.1 Simple pendulum. The Lagrangian is given by equals minus p where. Exercise 2.1. What are the equations of motion for the simple pendulum?
Example 2.2. The simple spring. Let's now consider where force isn't a constant but linear in some displacement. Such would be the case for a simple spring where F equals negative kx. Here k enters as a phenomenological parameter, not a simple dimensional parameter, and is material dependent. The equations of motion are thus. See the equation shown. Exercise 2.2. What is the Lagrangian? Example 2.3. The table spring problem. Consider a spring with one end attached on a table surface, the other end attached to a mass m. For planar motion in polar coordinates we have for kinetic energy T equals 1/2 times m times dot r squared plus r squared thet dot a squared. For potential energy, from Hooke's law, delta W equals negative k r delta r. The equations of motion then give m r minus m r thet dot a squared equals negative k r and d over dt times m r squared thet dot a equals 0. Exercise 2.3. Redo in rectilinear coordinates. The last example shows how familiarity manipulating differential equations will be helpful in what follows. For this reason, a review of ordinary differential equations is given in the appendix, App. A. With a brief overview in what immediately follows for convenience. Then, several more equation of motion and Lagrangian examples will be given in Sector 3.3.2, once we've learned how to deal with constraints.
2.3 Overview of simple trajectory-based ordinary differential equations. Some brief comments on the role ordinary differential equations, ODEs, at this early juncture are now given, with more background and numerous examples given in Appendix A. For what follows we are interested in forces that are polynomial in displacement, and at low order, thus ma equals F becomes ma equals 0, ma equals constant, or ma equals kx, as already mentioned. Since A equals x, we see that we are describing the family of ODEs involving second-order derivatives. Missing from a more general form of such an ODE would be first-order derivative terms, and in adding such we've now included standard frictional forces, if linear in first derivative and negative. Thus we find, almost effortlessly, how added terms in the ODE relate to physics, kinematics, and phenomenology, and can even be used by such, in reverse, to identify new physical effects, as done by Landau and Lifshitz in the discovery of the LL equation, and in categorizing various coupling phenomenon. Further analysis of the interplay of ODEs and phenomenology, together with dimensional analysis, is given in Chapter 9.